Welcome everyone. You are signed on to the Rotronic Instrument Corporation webinar, Calibration for Humidity Instruments. These Rotronic webinars are designed to help you make a more reliable, repeatable, and accurate measurement of humidity. And calibration is, of course, a key component to making one of those better measurements. Everyone who registered for the webinar will get a copy of the recording, a link to the recording, and a copy of the slide deck, and we deliver this two ways. The first is via an email to everybody who registered and attended tomorrow, usually within about 24 hours of this live broadcast. And we also post it on the Rotronic website. It's rotronic.com. Just look for the Academy section. Everyone out there is in listen-only mode. That means you cannot speak to us directly through your computer or through your telephone, but we do want to hear from you. We want to hear your questions and your comments, and the way to do that is to find the questions panel in your control panel for GoToWebinar and type in a comment or a question at any time, and we will have 2 Q&A sessions during this webinar, but you don't have to wait until then to type in your question. As it comes to mind, type it in, and then we'll queue those up during the Q&A sessions. We do have 3 great handouts for you. If you also look in your control panel and you find the handouts section, we've got the NPL Guide to Humidity. It's a fantastic basic, gives you a basic understanding of everything about measuring humidity. We got the NPL Beginner's Guide for Uncertainty, and we've got a psychrometric chart. It's an imperial unit chart for sea level. This webinar is presented and produced by Rotronic Instrument Corporation. If you don't know Rotronic, Rotronic manufactures precision measurement instruments for parameters like humidity, of course, carbon dioxide, dew point, temperature, water activity, and a few others. It also offers a state-of-the-art and leading-edge monitoring system for controlled environments. We don't talk about these products or the monitoring system during the webinar other than that little announcement, because this is educational. But if you do have questions about the instruments or the monitoring system, please, we'd be delighted to discuss them. Just shoot us an email or look up your sales representative on the contact page on the website. Speaking today, my name is Bruce McDuffie. I'm with the Rotronic Marketing Department, and I've been in the humidity measurement business for about the last decade. I've taught a lot of humidity measurement seminars and webinars, and over about the last 10 years. Michael Botskis is your co-presenter today, and Michael is a metrologist, and he works with Rotronic, and he specializes in relative humidity and temperature measurement. And Michael's been involved in manufacturing and calibration of humidity and temperature for about the past 100 years. No, 19 years. Welcome, Michael.
Thanks, Bruce. It's great to be here.
Sorry about that slip of the tongue there.
Okay.
Folks, before we get started, it's always interesting to know who else is out there. We've got a couple of 100 people listening in today. So I have a few questions to warm you up with the question and answer section and the polling feature. So the first question I have for you, this should show up in your presentation now, is what is your industry? Let's go ahead and choose the industry where you work. If you're on one of the other that's not listed here, feel free to type in the industry you work in, and we'll share that with the audience as well. I'll give you a few seconds for that. Once again, Michael, other is winning by a landslide.
It sure seems to be taking off, that's for sure. Too bad they limit the number of options we can put on this.
I know, that's the problem. So we've got some in the question pane. We've got dairy, research and development coming in. It's like pharmaceutical is out there, pretty next winning category.
Yeah, quite a few food production people as well.
Yeah. I'll go ahead and close that out. And I'll share the results so everyone can see. Got some other industries coming in the question pane. We got environmental risk management, aerospace, distributor, HERS rating, building diagnostics. I haven't heard that one, Michael.
No.
Metrological or meteorological, sorry. It's an easy one to
Slightly different field.
All right, thanks, folks. And another question for the audience. This helps us with our presentation, is what is your level of experience with humidity calibration? Are you an expert, enough to get the job done, but need to be better? Novice, just learning, first exposure maybe to humidity calibration, or you're not sure where you fall in the spectrum? Give that a few
Looks like
seconds.
a pretty good mix.
Yeah. Got a couple of experts out there. Got some good. This presentation should be just about right for the enough to get the job done and the novices. Experts out there, it might be a little basic for you, but who knows? You might even pick up something. I'll go ahead and close out the poll. Share the results with everyone. Good. Nice mix today. And the last question before we get into the presentation, what is your role? Should be showing up here in a second. What is your role? Are you the boss, calibration technician, lab manager, working quality, or something else? And again, if you're other, feel free to type it into the question pane there. Give it a few seconds. We've got a lot of material to cover today, so I hope you don't feel like I'm rushing through the fun part here. Go ahead and close it out. Share the results. Good, got a good mix. A couple of experts out there, Michael.
It's okay. Can keep us on our toes.
We got sales director out there, research professor, process engineering and calibration, instrumentation engineer, consultant to real estate property, QA. Good. Thanks for sharing that information, everybody. We appreciate that, and I hope you find that interesting for yourselves as well. Okay, and with that, again, thanks folks for sharing that. I'm going to turn it over to Michael and to go over what we will cover today and what we hope you get out of it.
Thanks, Bruce. So the goal of today is to give everyone a relatively high-level view of calibration of humidity instruments. We're going to start off by going through some of the terms and definitions that are important to this topic, and then we're going to get into the different approaches that can be that people can take to calibrating instruments, whether that be a field calibration or a lab calibration. There's a lot of different ways of performing these a humidity calibration. We'll take a look at some of the relative humidity generation technologies, so how we would create our relative humidity set points, and then we'll look at some best practices to go along with those technologies. So what are some of the key considerations we need to make when performing a humidity calibration? We'll take a look at accredited calibrations and why those might be important to us, as well as looking at some of the key information that we want to get out of the calibration process. We're obviously doing this calibration for a reason. What are some of the key things to get out of it beyond just a piece of paper saying that this instrument's good to go? So some of the key takeaways that we want for everyone today is to understand that a proper calibration means a better measurement and means that you'll be able to, or the end user will be able to make a better measurement with their instruments. It's also important for us to understand that not all calibrations are equal. There are different methods being used here, and just because you use one of them, it doesn't mean that an instrument will be calibrated to meet manufacturer's spec. It's important to take the best practices into account and to consider the uncertainties of the different reference equipment. And hopefully you'll be able to tell the difference between a good calibration or a low uncertainty calibration and one that has a higher uncertainty and might not be suitable for the end user. So with that in mind, I'll pass it over to Bruce now to go through some terms and definitions.
Terms and definitions, there's a few important ones to be aware of. These three terms showing on your screen now are probably the most misunderstood or miscategorized, if you will. First, and it's important to know the difference. First, the term calibration. This is where you compare the output of measurement, compare the output of the measurement instrument to a reference instrument and report the result. The confusion comes in because the service offered by laboratories, or when you talk about the service, it's called calibration, and many times that includes a calibration and an adjustment. An adjustment is where you change the reading of the instrument that's being calibrated to match the reference. So it's important when you send your instrument out for the service that's called calibration that you clarify if it includes an adjustment. For example, if you send an instrument up to NIST for calibration, they're not going to adjust it. They're just going to do a pure calibration. And the third term is specification. Just because an instrument has a specification does not mean that it performs to that specification. A specification is just a statement. Here's how the instrument should perform. And the only way you know that the instrument meets the specification is to do a calibration. And then you may have to adjust depending on the result. And now let's have Michael discuss the very important term, traceability.
So when people ask for calibrations, I've heard a number of different terms used to describe traceability. People will ask for a NIST cert, or I've heard I want to get my instrument NISTed, or I want a traceable calibration. Now, what is traceability, or what are people asking for here? And really what's being asked for is they want traceability of their instrument back to the fundamental definitions of what that parameter is. Now, technically that's not going back to NIST's definitions of it. It's actually back to what the global definitions are for what's termed the SI units. And those are maintained and defined by a group called the BIPM that's actually located over in France. But we get traceability through our national laboratories, and that's where the NIST traceable comes in. So when we're saying we want something to be NIST traceable, we're looking for metrological traceability to NIST's practical realization of the definition of that particular parameter, whether it be relative humidity or mass or temperature. Now, metrological traceability is a term that not a whole lot of people are familiar with. Most people view traceability to just be, as long as my instrument was calibrated with an instrument that was calibrated eventually by an instrument calibrated by NIST, we have traceability. But metrological traceability actually goes beyond that. Metrological traceability, you've got that unbroken chain of calibrations, and it's got to be a documented chain of calibrations going back to NIST. But in each link of the chain, you need to know what the contributing measurement uncertainty is. Without knowing the measurement uncertainty at each point in the chain, you really don't know how good of a calibration you've got for the final instrument. And this is a key point to bring out, because most traceability and a lot of calibration certificates without a measurement uncertainty on them, you don't truly have proper traceability because you don't know what the measurement uncertainty of your instrument is. Moving on to some other terms, uncertainty, which I just mentioned, is another key one for us to understand. And the uncertainty of measurement is the amount of dispersion that we might have over a measured result. So we get a measured result, but how much uncertainty is there in that actual result? And this often will get calculated or estimated by a calibration lab and put on the certificate, but then end users often will need to add to that maybe long-term drift or some other uncertainty components that the laboratory might not know for that specific instrument. So all of these build into the overall uncertainty. One of the handouts that Bruce has provided for us today actually provides a more detailed introduction to uncertainty and estimating uncertainty. So I encourage everyone to take a look at that. Accuracy is another term. Quite often, accuracy and uncertainty, people will interchange those. They'll say an instrument has an accuracy of a given value, 1% relative humidity, for example. And they might say, well, okay, so my uncertainty of this measurement is 1% uncertainty. And sometimes they can be used together. More correctly though, accuracy is typically a component of uncertainty, because the definition of accuracy in this case is essentially the closeness between the measured value and the reference value or the known value. So it's essentially the error or difference between those two values. So it's a component of our overall uncertainty, but it doesn't cover everything. Another term that's starting to be used more, and you might start to run into this especially with accredited calibrations, is the concept of false accept risk. And this is the risk that a calibration result that's reported in tolerance is actually out of tolerance. And this is because there is uncertainty in every measurement. And so if those uncertainty bars essentially go beyond the tolerance limit, there's always going to be some risk that that instrument's actually outside of tolerance. So we've got the concept of false accept risk. And we'll talk a little bit more about that near the end of today's presentation. Bruce, can you maybe guide us through a few of the common approaches to calibration?
Yes, there's two primary approaches to calibration. One is that we're going to talk about today, and we're not going to go into a depth of the actual process, just the pros and cons of each one, so we're aware of what they are. The first one is a lab calibration, and obviously this is where you remove an instrument or you take an instrument out of its normal place and you send it to a controlled laboratory space. The pros, the positive aspects of this are that a laboratory is a stable space. It has a fixed environment. Typically the temperature and the relative humidity are controlled and managed. And the processes are controlled too, because you've got technicians in a familiar space doing a repeated process. So ultimately, because everything is controlled and more fixed, you're going to have lower uncertainties and less chance of any kind of problem coming out of the lab. But on the negative side for lab calibration, you do have to remove the instrument or take it off site or remove it from its regular location and send it to the lab environment. This could mean time out of service, it could mean your production is down if it's a single instrument, could mean you have to engage your facility maintenance people to actually put it into some kind of a process or calendar. It just takes time and it's more inconvenient than a field process, which is the next one. Field calibration means you actually go out into the field where the instrument is located, in situ in many cases, and you do the calibration right there, sometimes even in the process or at least very close to the point of measure. The positive of this is you can usually do it without interrupting operations. Typically a field calibration is faster than a lab calibration simply because of you don't have to ship it anywhere. You don't have to take that time to move it around. But on the negative side of field calibrations, there's more variables. You've got a higher variable because you may be moving the generator, you may be using different people in the field, different references. You really have to have a very tight process, documented process, to have a high quality field calibration. So you do probably have higher uncertainties. It's harder to control the environment, and it requires a lot more training of the technicians, which may or may not occur.
One of the other key things for field calibration is quite often you might not get the same range of measurement that you would in a laboratory. In order to do some of the more extreme calibration points, the equipment just isn't portable anymore. So that sort of brings us full circle back to where you might want to consider laboratory calibrations.
Exactly. Thanks for that input, Michael. And folks, we have our first quiz now. And hope everybody was paying attention, not doing your emails or anything out there. I know this is highly exciting stuff. Calibration is defined, this is true or false. Calibration is defined as comparing the output to a reference and adjusting the output to match and issuing a report. So calibration is defined as comparing the output of an instrument under test to a reference, adjusting that output to match, and then writing a report. Give it a few seconds here. Some people may dispute this, Michael, but the pure definition of calibration is, it is what it is.
I think there's a difference between the definition and the expectation, and this is one of the challenges that a lot of calibration labs have in talking to customers about this.
Yeah. Yeah, I'll close the poll or the quiz and share the results. And the answer is false. Remember, we just went over calibration is just comparing the output to a reference and issuing a report. And again, I know it's a little bit ambiguous because a service called calibration maybe could be argued is different than the term calibration. But we can have that debate some other day, right, Michael?
That's right.
Okay, and with that, let's see, did I hide the, yep, there we go. We're going to talk about humidity generation technologies. We have 3 of them to discuss, and Michael's going to start off with saturated salts.
Okay, thank you, Bruce. So, as Bruce mentioned, the first generation technology is probably the easiest one to use initially and can be relatively flexible for us, and that's saturated salt solutions. So for a saturated salt solution, essentially what you've got, you take a pure water, distilled or deionized, something like that, and you add a specific salt to it. You put that into a closed container and let it come to equilibrium. What will happen is the airspace above that water will settle to a specific relative humidity depending on what type of salt is used in your saturated salt solution. Multiple salt baths, they're typically called a salt bath, can be used to then create various different relative humidities that let you then calibrate an instrument over a relatively large range of relative humidity. There's a couple advantages to the saturated salt solutions. They are a very low cost. You're essentially looking at a container to hold your salt bath in, water, and a salt. So it's a nice self-contained piece, can be very portable, easy to move around to wherever you need it. Some of the negatives and trade-offs to the saturated salt is, of the generation technologies we're going to talk about today, these have the highest uncertainties. There's typically not going to be any temperature control of the salt bath, so you've got temperature gradients within the bath which are going to lead to uncertainty in the relative humidity value. The salts and water are also very sensitive to contamination, so one salt bath isn't going to be good for an extended period of time. It's not going to last for a year, for example. It might need to be replenished once a month or on some other basis depending on what contaminants get into it. Not only the salts and the water can get contaminated, but I think most people that have used one of these have probably contaminated their probes at one point or another. A little jostle of the salt bath or inserting a probe a little too deep, and suddenly you've got salt water on your sensor, which would then need to be cleaned off because it will cause shift in readings to most sensors, if not damaging them permanently. So you've got risk of contamination that way as well. And then you need to have multiple salt baths to do multiple points. So this really doesn't make it an automatable process. It is very manual, and you need to manually put the probes from one bath to another, check to see when they stabilize. So it can take a bit of time. You might use this if you're okay with the high uncertainties, or if you need to do a spot check in a location where you just can't take one of the other generators. The salts might be a good solution for you.
Yeah, I've dipped a probe or two into salt baths over my days, Michael.
I know in my early days, ours were in the way where you could drop the whole unit in, and I had one or two go that way. The next technology to look at is the divided flow generators. And in these generators, they essentially have a capacitive RH sensor in them typically, and that is that's used to control the environment. It's looking to see, okay, what is my humidity in here above or below my set point? And depending on that decision, it will run air either through a humidification process or a dehumidification process until the chamber comes to the right relative humidity. And in doing that, these chambers can be very quick to respond. And then the reference on them is either the capacitive sensor that's used to control them, or sometimes a chilled mirror could be either used as the control sensor and the reference, or it could be an external chilled mirror to monitor these generators. There's a lot of these coming on the market now, and a bunch of them can be lower cost. So starting in several $1,000s, you can get a divided flow generator, but the range for them does go up quite high depending on the options and features selected. They are self-contained, so it is a standalone box that can do the generation, and it can do a fairly wide range of relative humidity points. Quite often these units are specified from about 5% relative humidity up to 90 or 95%. Generally these are portable devices or considered portable, but several of the ones out there now can be quite large benchtop units that are staying put. Typically these have some of the fastest response times of the different generators that we're talking about today. So your response time, depending on the size of the chamber, might be 5 or 10 minutes. You might get to a relatively stable point, rather than some of the other technologies where it could be several hours. Depending on the features of the generator, there might also be the allowance for some automation so that you can plug your units in, program it to do several humidity points, and let it run. The trade-off for these generators, the uncertainties are in the mid-range. They're not the best, but they typically can be better than salts, especially if you add on a chilled mirror as the reference. Depending on the unit, they're not always temperature controlled, and without that temperature control, of course, we're going to get larger uncertainties because we're going to have temperature gradients and instability within the test chamber itself, and this leads to relative humidity gradients and instabilities. So these generators, they're getting quite common, especially for field calibration type applications, but they're also used in a number of laboratories as well. If speed is the critical factor, this is probably the technology to use. And if you're looking for a smaller device, these are probably the smallest active generators out there. Bruce, I'll pass it off to you to discuss the two-pressure generators.
Two-pressure generators are exactly that. They use two pressures to generate different levels of relative humidity. If we recall back to our relative humidity basics or theory class, and by the way, if you missed that, you can watch the on-demand recording at the Rotronic Measurement Academy online. But if you recall Dalton's law of partial pressures, and basically, without going into it in detail, if the relative humidity does change proportionately to the actual pressure difference. So the way these work is you compress air to a higher pressure, whether it's 50 or 100, whatever the PSI, the gauge pressure is, and you saturate it. So you know you have air at a specific pressure and it's 100% relative humidity. Then it goes through a pressure reducing valve, and isothermally we expand or lower the pressure, usually to atmospheric. And that pressure difference is calculated or measured very accurately, and because we know a very specific pressure difference, we also know the temperature hasn't changed or as much as it changes, we can calculate a very exact relative humidity. And that's how those work. They're very accurate, but the pros and cons are that they're very expensive. So other positive aspects of a two-pressure generator, you can get very low uncertainties for your relative humidity. they are not sensitive to sensor drift because they're relying on pressure and temperature measurements. There's no relative humidity measurement involved. And they do allow for some nice automation, and you don't have to have a separate reference, because if you get traceability to your temperature sensor and pressure sensors, then because we have an accepted formula to calculate relative humidity, we don't need to have a relative humidity sensor involved. As I mentioned, they are pretty expensive. You do have to have very clean, high pressure air, so it means you have to dry it to about -40 dew point and have it go through a number of filters, which can be an expensive system, or you use nitrogen. Response time to change from one level of relative humidity to another can take a while, so it's going to increase the time to get your calibration completed. And because the airflow rates are so minimal inside the chamber, even the sensors, when you do change to different levels of relative humidity, the sensor response time is going to be slower. If you have a controlled environment like a laboratory and you need very low uncertainties, this is a good solution. And I think that brings us up to our first Q&A session, Michael. Yep, it does. And we've got quite a few coming in here. And let me see if I can get them up here. Okay, here's a question from Oscar. Oscar says, do you sell all these machines? That's a good, thanks for that, Oscar. We'll send the check in the mail for that one. The answer is yes, Rotronic does sell a very good calibration mixed flow generator and associated chilled mirrors and calibration services that are accredited.
We don't sell a two-pressure system. However, in our lab, we do actually use all three of those technologies for humidity calibrate. Excuse me, for humidity calibration. We've got saturated salts, a two-pressure system, and a divided flow system.
Here's a good question, Michael, from Ian. What is the uncertainty you can expect from a saturated salt solution?
That is a good question, and the answer is it depends, which is my favorite answer out there. Different salts will have a different uncertainty associated with them. There's tables available out there that define the specific salts that generate the specific relative humidity points, and those tables include an uncertainty associated with each salt. So depending on the salt used, it's going to have a different uncertainty. On top of that uncertainty, though, would be issues like temperature uniformity and stability within the air above the saturated salt solution. But fundamentally, it's dependent on which salt it is, and then impurities in the water and salt will add to that as well.
Here's one, Michael. It's from Paul, and he's asking, can you share some typical uncertainties for each of those calibration methods? I think he means the generation technologies.
Sure. Putting these into an order of magnitude only, there are a number of factors, additional factors that come into play. Saturated salt solutions are typically going to be, I think the best ones claim around 1%, but can get as high as 3 or 4% RH uncertainty. Divided flow systems, if you've got a good chilled mirror on them, they can get down to less than 0.5%. But if you're using the control sensor as the reference, your more typical is going to be about 1.5 to 2% uncertainty, potentially even a little bit higher. And then a two-pressure system, those, for the really good ones, just as standalone, they can get to about 0.3% RH, but that's a $250,000 system. More typical is about 0.5% RH uncertainty from those. And that's just the base uncertainty of the chamber. It doesn't include things like gradients within the chambers as well. So those can add a little bit more, but you can also control those a little bit through doing things to make sure you've got a small and stable environment.
Good. Good summary, Michael. And we have time for one more question. And boy, the questions are coming in like crazy here. So keep them coming, folks. We'll get to as many as we can. This is from Gadiel. I think I said that right. Can an instrument be calibrated to tighter specifications than those stated by the manufacturer?
Yes, they can. You can always, the uncertainty of the instrument always ends up depending on your calibration. So if you take an instrument that's calibrated at the factory and has a given spec based on that calibration, and you calibrate it using a calibration process that has a lower uncertainty, potentially you can go and improve the overall performance. Another way of potentially improving the performance is to carefully track the long-term drift of that instrument. Manufacturers are specifying instruments so that the vast majority of them are going to be in tolerance over the calibration interval. If you know the drift of your instrument, you can potentially actually make a proper estimate specific to that instrument of what the drift is, and that could also help you make a determination that your uncertainty is less than what the factory specification is.
Good. Thanks for those questions, folks, and thanks for those great answers, Michael. And again, we have one other Q&A session towards the end, so I've got your questions here in the list. Keep them coming, and again, we'll get to as many as we can. With that, I'm going to turn it back over to Michael to talk about some best practices for humidity calibration.
Thanks, Bruce. And this is going to be fairly high level for the best practices. I highly encourage everyone, if you want more in-depth information on this, we've got another webinar that's available on the website about making the best possible relative humidity measurement. The information in that is also relevant to this because essentially what we're doing in the calibration is trying to make the best possible relative humidity measurement. So some of the best practices that we've got, and probably the most important one, is to properly allow everything to come to equilibrium. And I'm not just talking about water vapor or water content here. Temperature is a key parameter for any relative humidity calibration. Going back to Dalton's law and the definition of relative humidity, where we've got the amount of water in the air or the space above or open gaseous space versus the amount that space can hold, and the amount of water vapor that can be held in that space is temperature dependent. So if you don't have a stable and uniform temperature, you do not have a stable and uniform relative humidity. So everything you can do to improve the temperature stability and temperature uniformity improves the relative humidity uniformity and stability. So temperature and controlling temperature well is a key part of any relative humidity calibration. So on that, you want to make sure that you've got your sensors as close together as possible. And here again, the key thing is to reduce any temperature gradients between the two. You want to make sure you don't have any heat sources, and that heat source could even be coming down the stem of one of your relative humidity sensors if you're trying to calibrate it at an elevated temperature, but the handle of the probe, for example, is sitting outside a chamber at room temperature. So those are probably some of the biggest contributions to humidity uncertainty in a calibration after you've selected a particular generation mode. It can be important to read your results simultaneously. For example, if you're calibrating a probe in situ and reading the results off of a building management system or real-time monitoring system, those systems sometimes only update their readings every 5 or 10 minutes. And what you might end up getting is a reading from your unit under test and a reading from your reference that are 5 or 10 minutes apart, and suddenly they don't align very well, and in reality, it's the environment that's changed. You're not looking at an error between the two instruments. So make sure your readings are simultaneously, and ideally take an average of a number of samples. Choose your adjustment points carefully. Definitely look at what the manufacturers recommend for that, and understand that if you're calibrating over a small range, potentially if you're making adjustments, you're making that range better, but everything outside of that range might be made worse. So it's important to take that into consideration, especially if you're trying to shorten the amount of time your calibration takes by not having all the adjustment points. You have to understand that that instrument now, the accuracies might only apply to everything within that calibration range. Another thing that gets missed sometimes is to calibrate the analog signal of the instruments. Quite often, it's very easy for us to calibrate the digital output of an instrument or look at what it's displaying on the screen. But if that instrument is actually using the analog outputs to go to a building management system or something else, it's good to calibrate those as well to make sure that they are working properly. And it can be a good practice to spot check in between calibrations, and this can be going up to that sensor in the field with a handheld unit and going to make sure that it's reading correctly. There's some things we need to take into consideration when doing that to make sure that we're not affecting the readings by breathing on the sensors or staying too close to them and heating up the environment. But a spot check can be good to understand how your instrument is performing. And some people actually use that as the calibration of the instrument, but it has fairly limited use because you're only checking it at that one point.
And I think we have a quiz at this point, Michael.
Okay. I think you're right.
See, we'll bring it, bring a lot of the topics together here. Have it launch here in a second, and the question is, which of these statements is not true? And I'll tell you there's more than one in this list that is not true, and obviously you can pick more than one. Which of these statements is not true? A two-pressure generator provides very low uncertainty. Saturated salts are an inexpensive way to generate humidity. In field calibrations, fast speed of measurement is better. Always make the measurements as close as possible to each other. In other words, the reference and the probe. And always shield the probe from light with your body. Give this one a few more seconds because it takes a little more thought. The answers are coming in. I'm going to go ahead and close this out, folks. We are running a little bit short of time here. So last chance. Okay. I'll share the results. And the correct answer is that the third one, in-field calibrations, fast speed of measurement is better. That is not true. In any calibration or any measurement, take your time. Be thorough. Don't rush it. And the last one, always shield the probe from light with your body, is not true, because if your body is anywhere close to that measurement point when you're calibrating, it's going to throw the whole thing off because your body gives out a lot of water vapor and a lot of heat. Anything to add to that one, Michael? Should we go on?
I think we should keep going on.
Okay. Next topic next topic we're going to discuss is accredited calibrations. And Michael will share what they are and if you need one or not. Michael?
Thanks, Bruce. So if we're sending a unit out for calibrations to a lab, quite often we'll have the choice to choose between the lab's regular offering, or they might have an accredited offering. And it brings up the question, what is an accredited calibration and why would we want it? So accreditation, and typically we see accreditation to ISO 17025 for when we're talking about calibration. 17025 is slightly different than 9001. 17025 is an accreditation to prove the competence of a laboratory. So essentially a laboratory that has become accredited to a particular parameter has proven that they're competent to perform that calibration and that they can actually achieve the uncertainties that get reported on the calibration certificate. And this is checked in a couple different ways. They actually have to do what's called proficiency testing or interlaboratory comparisons to ensure that their readings are reasonable and within their uncertainties. But there's also a technical expert that would come from an organization like NAVLAP or A2LA who come in and audit these laboratories to ensure that they've got the processes in place, that they understand how to do measurement uncertainty estimations, that they've got the proper equipment in place and they know how to use it. So we might want accreditation. Perhaps your industry would require it, or your internal procedures require it. If you're an accredited lab, your internal procedures will require most likely that you use an accredited lab for all your calibrations, for all your reference equipment. Perhaps a regulatory body says, yes, we want to see accredited calibrations for everything, because when we've got the NAVLAP symbol or the A2LA symbol on there, we know you've got proper traceability of measurements. Or perhaps it could come down to credibility. Your quality system might say you need to do a quality check on all of your calibration vendors, and this might give you a way of saying, well, you know what, a third-party expert who knows more about that particular parameter than us has gone in, audited them, and said, yes, they know what they're doing. They've got everything that we would be looking for in place. So I can take that accreditation and not have to do that extra quality audit on that vendor. So those are all times where we might want to use an accredited calibration lab. The pros of them, generally it's going to be a very reliable calibration. That laboratory has third-party accountability. The accreditation bodies will suspend accreditation if the lab is doing things that they shouldn't be. You know the labs have an audited quality system in place, and that everything's documented and there's a proven calibration capability. And that capability gets proven on an ongoing basis. So there's a lot of confidence that you can have in the results of the accredited calibrations that you might not have from a regular calibration unless you've gone in and audited that vendor. On the con side, typically laboratories will charge more for the accredited calibration because it is more work for them quite often, and they have to go through these third-party audits. So that takes time and costs them extra money as well. Potentially the service can take longer. Sometimes that extra time though is worthwhile. The accreditation ensures that the calibration process is happening using best practices. So sometimes it's better for it to take longer because you know it's being done well. I will say though that just because a calibration is accredited does not mean it's got the lowest uncertainties. All it means is that there are uncertainties there and that those uncertainties have been proven to be a good estimate for the particular process used. So accredited calibrations can vary in their overall uncertainties. They're not all the same as well. And there's limited number of labs that are accredited, so you've got a smaller option of labs that can perform that accredited offering for you. Some of those labs may also be accredited for the field, but that's an even smaller number. So if you're looking for a field calibration and you want it to be accredited, your choices can be very limited.
Well, Michael, let's bring it all together for our audience and talk about the calibration itself. What is some key information that we should be looking for?
Okay. So within the calibration process, there's, to my mind, 3 key things that we're looking for. We want to see the as-found data. How has that instrument been performing up to now? And this gives us confidence that all the measurements that we've made and the decisions we made based on those are valid. If it's out of tolerance, we potentially have to go back and revisit those. The as-left data is the information for how that instrument is performing now, potentially after an adjustment. So what's my starting point going forward for my future measurements? The last piece of information that I view as one of the key pieces is the calibration uncertainty. This is required to give us the metrological traceability that we typically want out of a calibration, but it's also important for us to then understand essentially the quality of the calibration. So to what degree is this instrument performing? Does it have a 1% uncertainty, 2% RH uncertainty, or larger? So it gives us an idea of the accuracy is the wrong word, but the uncertainty that the instrument measurements will have going forward. It's also key for us to understand the false accept risk. And to introduce this topic a little bit, we don't have a whole lot of time to talk about it, so we'll give it a brief introduction. What we've got here is a diagram of possible measurement results. We've got a nominal value or a reference value, and then we've got sample measurement results that an instrument might give us. So these are all the results from our unit under test, and ideally we want them to fall within the manufacturer specification limits, which are these black lines here. On each measurement value, we've got an uncertainty associated with it, and this can be small or large depending on the process. So you can see as these values increase in error, so the difference between the measured value and the nominal value, the uncertainty bars actually can go beyond the specification limit. And so this brings us to the concept of, okay, what risk is there that some of these measurements are actually, or some of these instruments are actually outside of tolerance? And one of the ways that we limit that risk is to limit the false accept risk. And one of the standards, the ANSI Z540.3, actually states we want to limit that risk to a maximum of 2%. So one of the methods for doing this is to create a guard band. And this guard band here, hopefully you can see it as the green line, is calculated based on the size of the uncertainty values. And what we end up then is a situation where we've got past results, so where the measured value is less than that guard band limit, failed results where the measured result is outside the specification limit, but then also this indeterminate result. It's not that this result is a fail or a pass, it's that the laboratory can't state with less than 2% risk that it's a pass. So then it's up to the end user to determine what is the amount of risk I can deal with for this point. If I need to have less than 2% risk, I would need to call this a fail now. If I'm okay with the larger than 2% risk, I can call this a pass. Typically and classically, most end users would call this a pass, and most people I see still do, but 17025 requires that laboratories take uncertainty into account when reporting results, and this is one way now that we're seeing laboratories starting to do that. So if you're getting accredited calibrations, you're probably going to start to see something like this a little bit more often because the accreditation bodies are starting to be a little bit more demanding on how laboratories report results. And with that, I think that takes us into our last question period.
It does. And before we jump into questions, we've covered a lot of material here today, and we haven't covered some in detail. So my last question I have for you folks is, of these different topics, which one, if any, would you like us to be more detailed and do a complete hour webinar on this topic? So if you can choose one from the list here, and if you do choose other, if there's something else you'd like to see more detail in related to humidity measurement or calibration, please type it in the question pane. And we did do an entire webinar on traceability. Oh boy, it was about a year ago, wasn't it, Michael?
I think so, yeah.
That's available on demand, but it's always nice to do a fresh one too. So I think we probably could be up for that.
I would be up for it.
Okay, thanks folks for sharing and I'm going to go ahead and close this out. Looks like a lot of interest in a lot of topics, Michael. Wow, this is great.
It sure is.
Gives us a lot of material. And I'll go ahead and share that with everyone so you can see. Oops, I can't share that one. Oh, there it is.
Oh, that's come up.
Okay, good. Thanks for letting us know, and we will endeavor to do more details on these different topics. And with that, we've got time for a few questions here. Let's see, Michael, what do we have in the queue? Here's a good one. Other than the reference uncertainty, this is from Jamie, other than the reference uncertainty, which other factors affect the uncertainty on relative humidity calibration?
Okay, so there's the reference uncertainty. In addition to that, we would need to look at things like the resolution of the unit under test, as well as the precision or repeatability of the unit under test. Then we also need to look at the temperature gradients within the calibration environment. Often the reference uncertainty does not include temperature gradients inside our chamber, for example. So we need to know, we need to figure out what the relative humidity gradients are, and for that, if we know what the temperature gradients are, we can calculate out what the relative humidity gradients are. So those are some of the key additional factors. If we also want to, for the instrument in the long term, we would also want to have an understanding of what the long-term drift is of our unit under test, so that when we go to use it down the road, 6 months down the road, the uncertainty at that point is not the calibration uncertainty on the certificate. It's that uncertainty with a drift uncertainty added on to it.
Here's a good question from Robert, and I wonder this one myself. Would you consider a salt bath as a standard?
They can be considered as a standard. You need to go through, you need to make sure you've got a controlled process to create them, but they are considered a reference standard based on the tables. I believe they were done by Greenspan.
Greenspan, right.
Yeah, so those tables provide a known relative humidity for a given salt, given saturated salt solution. So those can be considered a standard.
Here's one from Nathaniel. Does the two-pressure generator have to be calibrated or traceable? And then is a QA/QC for it. I'm not sure what he means by that. But.
Absolutely, and any instrument like that does need to be calibrated and traceable. A two-pressure generator, though, it gets its traceability not through relative humidity. Typically, there won't be any direct relative humidity measurement inside the chamber. It gets it through the temperature sensors and the pressure sensors inside the chamber. So all those sensors get calibrated and are traceable, and that gives you the traceable relative humidity readings.
There's been a couple of questions about calibration interval. Michael, how do you know what your calibration interval should be?
Well, I'm going to go back to my favorite answer of, well, it depends. And one of the first things to look at when trying to determine a calibration interval is, what does the manufacturer recommend? That recommendation is probably a good starting point. After that, though, the end user needs to take a look at a couple of different factors. Ideally, if you've got some history on the instrument, you would want to look at that instrument history. If it's always out of tolerance after 1 year, for example, then you want to potentially look at either reducing the calibration interval or expanding your acceptance limits. If you don't have any of that history, you can't necessarily, you're left with the choice. Either you use the manufacturer's recommendation, or perhaps if you're in a very critical situation, you start with a very short calibration interval, and once the instrument starts to prove that it can be stable for that period, you start extending it. So the answer in the end comes down to the end user making a decision. Most people use the manufacturer recommended interval, but it would be good to look at other factors as well.
Very good. We're about out of time here, folks, so thanks very much for those questions. We still have a lot we did not get to, Michael, so we'll make sure we get back to you guys via email. And we're going to skip the takeaways here. You guys know what your takeaways are. And just to wrap up, the Measurement Academy has a lot of more information, as we mentioned, webinars on demand. Check that out on the website. Just go to the Academy, Measurement Academy section. A survey will pop up for you guys still on. Just let us know how we did. Michael and I love to hear how great we did, but we also love to hear how we could make this better for you, more useful. Thank you again, everyone, for spending time with us today, taking time out of your busy day to learn about calibration of the humidity instrument with Rotronic. And thank you, Michael, for your great expertise.
Thank you, Bruce, and thanks everyone for joining us.